So far we have been studying the non-smooth bifurcation phenomena that will occur in one dimension or two dimensional maps, and we will go to more details of it, but before that, before going to that stage, let us take stock of where we are. Essentially, I said that there are a large number of physical systems, physical and engineering systems, which when modeled in a discrete way give rise to piecewise smooth maps. And therefore, in order to understand the bifurcations occurring in them, you will have to understand the bifurcation that can occur in a piecewise smooth map. And then we say that in the neighborhood of the border collision event, we have if we want to understand what exactly happens, we can locally linearize that the state space around that border crossing point, and thereby we obtained the normal form, and then we went on analyzing that normal form, and we have gone on and on and on. So, let us come back and figure out where we are. Our objective was that we should be able to explain the bifurcations occurring in such systems, and so based on whatever we have learnt regarding the character of the bifurcations, the different types of border collision bifurcation that can take place, and so on and so forth, can we now explain mathematically the bifurcation that we actually observe in systems. For example, if you observe that in a system, in a physical system, now I am not talking about the normal form now. Suppose a bifurcation diagram is observed which goes like this. Then based on what we have learnt, can we infer anything about what is happening here? Obviously, we can see that there is a sharp bend in the bifurcation diagram, and if the map is smooth, we do not expect this kind of a bend, right. So, if we encounter such a bend where before the bend and after the bend the behavior is period 1 or some other periodicity, but nevertheless there is a bend, then based on what we have learned, we would say that no, at this point there has been some non-smooth phenomenon occurring, and that should fall under the category of the border collision bifurcation, where a stable periodic fixed point hits the border and still remains a stable periodic fixed point. And in order to explain that, we will have to obtain the eigenvalues just before and just after this event. So, with these two arrows I am showing that at these 2 points, just before and just after, we will analyze the fixed point, we will obtain the eigenvalues, and then if we do so, we will notice that the eigenvalues have jumped, but again from inside the unit circle to inside the unit circle. So, it might be something like this. I am just schematically showing it, but it could be anything else also. Say initially it was something like this, these 2 fixed points, and they jump to these 2 positions, still it is stable, right. So, this kind of phenomena, then if we encounter, we will be able to explain in terms of the physics that we have learned. What if we encounter something like this? And so on and so forth. What will we say about this? Here, as you can see, there was again a bend at which a period 2 orbit remained a period 2 orbit. So, in order to explain that, we will need to take the second iterate of the map. That means, from the original system we have obtained the map. Now, we will take a second iterate and apply the same logic. If you take the second iterate, then it is simply something like this. Okay. If you take the second iterate, this will be second iterate, remember, then this will be period 1. So, it will, you will see just one point, and then you will have to obtain the eigenvalues at this point, these 2 points, and if you obtain the eigenvalues of the second iterate, then you will again encounter the same kind of situation that the eigenvalues initially were inside the unit circle, they jumped discretely, they changed discretely, but still they remain inside the unit circle. But that logic will now be applicable to the second iterate of the map, not the first iterate. Okay. And you might say, you might do that by simply obtaining the eigenvalues of the fixed point that is here, another fixed point that is here, the Jacobian matrices, multiply the Jacobian matrices, you get the Jacobian matrix of the second iterate. If you analyze that, you will get this behavior. On the computer screen, if you see the computer screen, I am drawing a bifurcation diagram, and that is the bifurcation diagram of the boost converter. Can you see what is happening? Okay, you might see that here this is again drawn by dynamics. So, it is the bifurcation diagram drawn from the top to bottom. So, from the top to bottom. Can you see the mouse? Yes. So, from here a period 1 orbit starts, and the parameter, in this case the load resistance, has been varied from 100 ohm to total 600 ohm. So, up to say something like 300 ohm, it was a period 1 orbit. So, there is a range of the parameter load resistance for which the periodic orbit remains. And at this point what has happened? At this point what has happened? It is a smooth period doubling, a normal smooth period doubling. So, just by the appearance of it, you will be able to infer, just by the appearance of it, you will be able to infer that this is a event where the eigenvalue of the period 1 orbit became -1. So, following this event, the 2 branches of the period 2 orbit diverge from each other, and then something very peculiar happens here. Can you see this? At this point and at this point, something very peculiar happens, because now the orbit suddenly becomes chaotic. Let me draw this, because this is too narrow lines. So, let me draw this here, which will make it clearer. It was like this, and then it underwent normal period doubling bifurcation, but at this point it became chaotic. So, how would we explain this event? Now, you can see that here is a period 2 orbit that suddenly underwent a transformation, and obviously this event you can easily see that that cannot be a smooth event, it cannot be a smooth bifurcation. So, that has to be a border collision event, but what actually happened? So, at this point a period 2 orbit hit the border. So, in order to explain it, we will have to consider the second iterate of the map, and that second iterate, one of the points of the second iterate map hit the border. So, imagine that the border was here and it was hit. So, following that, I can see that it went into a 2-piece chaotic orbit, and then after some time these 2 pieces merged. So, if you look at it from the point of view of the second iterate map, you would be able to see something like this. Right. So, if you start in the normal form, then it would be something like this, that a period 1 orbit hit the border, and then it became a 2-piece chaotic orbit. in general it is a transition from periodic orbit to a chaotic orbit. And when did that happen? Under what condition did that happen? We have earlier seen that it happens in so this is our tau L axis and this is our tau R axis, and we found that that happens somewhere here. Okay. In this part there is a transition from periodic orbit to a chaotic orbit, not in this part, because here it is a transition from no fixed point to a chaotic orbit. So, somewhere here, and we have seen that in this part we have the period 2 orbit, and then you have period 3 orbit and period 4 orbit. In between you have the chaotic orbits. Okay. So, this in this case, if you try to analyze it, then it should be explainable by means of that part, that theory, if you want to analyze it. But how do you analyze it? Essentially, in order to analyze, what you have to do is to take the second iterate of the map, obtain the Jacobian matrix of the fixed point just before the border collision happened. But after the border collision happened, what happens? You do not have the period 2 orbit any further, it is a chaotic orbit. So, whose Jacobian will you find out? In fact, inside this chaotic orbit there will be a unstable period 2 orbit. So, the essential point is that in this case also, when we are trying to study, what we did, we studied the eigenvalues of the period 2 orbit before and after the border collision event. Here also, even though you do not see in a salient way the period 2 orbit, you should know that it must be there, and your job is to find out the Jacobian of the period 2 orbit, and then and only then you will be able to fit into this theory. So, the way it is done is that you will obtain the Jacobian of the period 2 orbit before and after. How to locate that unstable periodic orbit, I will come to that later. You will need to locate that unstable periodic orbit, and then on that you will have to calculate the Jacobian. Once you have calculated the Jacobian, what are we doing? We are obtaining the trace and the determinant. Okay. Now, from the original system we have obtained the trace and the determinant, but the strength of this theory is that these two quantities, the trace and the determinant, are invariant under coordinate transformation. So, when we transform it into the normal form, these two quantities do not change. So, if we from the original system obtain the trace and the determinant, we can thumb the table and say that okay, I have got the right trace and the determinant for the normal form also. And then we will say that okay, for the particular parameter that I have chosen, it falls here, and from a theory we can see that it must lead to the transition from a periodic orbit to a chaotic orbit, and that is exactly what happens. Clear? Let us give you one more example to illustrate what we mean. Say you encounter a bifurcation diagram something like this. Say it goes through another set of period doubling. I wish to draw it like this. That means acute angles, and then and finally it becomes chaotic. Okay. So, at this point what happened? There was a period doubling, but the branches that emerged out of it went in acute angles, which is not a characteristic of smooth systems. So, by looking at it you should be able to infer that it is a non-smooth period doubling. Okay. So, in order to analyze this, what will you do? You will obtain the eigenvalues just before the border collision. Whose eigenvalues? Period 2 orbit. that means the second iterate of the map. After the border correspondence, whose eigenvalues you will find out? Now it is period 4. No, you will not obtain the eigenvalues of period 4 map. You will obtain the eigenvalues of the same iterate. That means, earlier it was the second iterate, now also you will have to locate the period 2 orbit, which will be going like this, unstable period 2 orbit. You will have to obtain the eigenvalues of that. And then once you have done that, you will be able to show that it satisfies the condition where we have already shown that there will be a transition from a periodic orbit to a period 2 orbit, higher periodic orbit. Let us go one step further. Suppose after this you have encountered that in a smooth system, after it goes into chaotic, there are periodic windows, right? You have encountered that. Now, in this case also, in non-smooth system also there can be periodic windows, but suppose you find that the periodic windows are like this. Not really periodic windows. Most of you who study literature in this field will come across bifurcation diagrams looking like this. What will you say about that? We know that such periodic windows are normally created in a smooth map by saddle node bifurcations, where a new periodic orbit is born. Now, while we were studying the non-smooth systems, we also learned that a saddle node, a non-smooth saddle node bifurcation can also lead to a situation where both are unstable. If both are unstable, then there is a possibility that the resulting orbit will be chaotic. Okay. So, you should immediately realize that that is exactly what is happening here. Here there has been a birth of a periodic orbit, not only one pair of periodic orbits, but both unstable, and as a result around that there has been a chaotic orbit, that is new chaotic orbit that has been born. And because of the birth of this new chaotic orbit, you see this window, which is not a periodic window, it is also a chaotic window, but a different chaotic window than this. But remember, here there are 3 bands that are going, right. At 3 points I can see that it has been born. What does it mean? It means that this is the event happening in the third iterate of the map. So, you will have to look at the third iterate of the map, and if you do so, you will find that there are 2 fixed points, there must be. I mean, the theory says that there must be. By closing your eyes, you can say that you can thumb the table and say that there must be 2 different unstable period 3 orbits. 2 different unstable period 3 orbits that has been born at this point. So, the way to analyze it, locate these period 3 orbits, find out their eigenvalues, and then fit into the theory. Where do you expect it to be? You expect it to be somewhere here in this part, right, where you know that the bifurcation is from no orbit to a chaotic orbit. So, seen in the third iterate, it will be no orbit to a chaotic orbit, it will be like this. There was nothing before that. At this point, 2 periodic orbits were born, both unstable. Both unstable, but what is the difference between them? One a regular saddle, another a flip saddle. So, even though both unstable, you can easily figure out what kind of orbits are they. So, one will be a regular saddle, another will be a flip saddle, and then the bifurcation diagram individually seen from the point of view of the normal form will be like this, and seen from the point of view of the actual system, it will be like this. So, the explanation of this kind of an event will have to be obtained by the theory of the non-smooth maps. Clear? We have also come across situations where what actually happens here? What happens here is that you have the birth of a period periodic unstable orbit, another two unstable orbits, one regular saddle, another flip saddle, but the chaotic orbit is not stable. That is what happens here. In this part it is stable, in this part it is not stable because in between there has been a boundary crisis. So, this fellow is unstable. So, you would not say that nothing happens here, you would say that if the parameter range is here, then it leads to the creation of an unstable chaotic orbit. Okay. Now, unstable chaotic orbit being created, you might argue that so what, it is not there anyway. No, it is not true that it is not there. The point is that these unstable chaotic orbits may later in the bifurcation diagram have its own influence, because at some point of time it may take part in an interior crisis, so that suddenly you will find the attractors enlarging into something you do not know what. But the point is that that orbit was created some time back in this kind of a bifurcation, which you did not notice because it was not observable. But theory will prompt you to say that no, in such a system it is possible to have the birth of unstable chaotic orbit, which will have its own influence on the dynamics later if it somehow encounters a interior crisis. Just to recall, when interior crisis happens, when the existing stable periodic orbit somehow contacts with that unstable chaotic orbit, then the whole chaotic orbit becomes stable. Under that condition, you will find that suddenly something that was not there appearing into the picture, and often we are very hard put to explain how, where did this fellow come from. This actually came from this kind of an event. Okay. So, we have more or less understood. What will you say if you have a ongoing chaotic orbit, chaotic behavior, say at this point it terminated and you have this in a piecewise smooth system? What will you say? This event could be, since it is a piecewise smooth system, this could be related to a smooth bifurcation, smooth saddle node bifurcation, or it could be a non-smooth bifurcation where the parameters are here. If they are here, then what is the character? It is like a saddle node bifurcation where a pair of stable and unstable fixed points are bound. The stable fixed point will be visible. If you have something like this, you would say that similar thing is happening in the third iterate. Okay. But no, you will have to test that. Why? Because such a thing could be, as in the logistic map you have the period 3 window created by a saddle node bifurcation, here also it could be so. So, how to distinguish between them? You will have to say that at this point not only this fellow has been born, but another fellow has been born which is unstable. You cannot have this orbit otherwise, right. So, just following this you obtain the eigenvalues of these two orbits, a period 3 stable orbit and locate a period 3 unstable orbit, because you know from theory that it must be there. Locate the period 3 unstable orbit and find out their eigenvalues. Now, what happens in a smooth system? In a smooth system, if you have this is the, if we assume that this is the chaotic orbit and at this point there is a birth, then it will be born like this and then the other orbit will be going like this. Here these two are going at this point in a orthogonal direction, but here it is acute angle, but this is sometimes difficult to identify. So, as you go closer and closer, these two fixed points come closer and closer, and then at this point they have the same eigenvalues, not here. Here as you go closer and closer, these fellows eigenvalues will remain different. That is the characteristic of the non-smooth saddle node bifurcation, where two orbits have been born, but you notice that one with the eigenvalue placed such that the tau L is greater than 1 plus delta L, and the other with the tau r between plus 1 plus delta r and minus 1 plus delta r. They are different, and they are different at this point itself. Okay. So, by examining that, we would be able to infer whether it is a smooth saddle node bifurcation or a non-smooth saddle node kind of bifurcation, where a parameter is placed here. Clear? So, basically my point is that all this theory based on the normal form is fine, but do not be carried to think that it is just a mathematical exercise. It is essentially an exercise by which we will try to explain phenomena that actually happen in physical systems. Okay, now let us come to the middle part, which I said may show some surprise. This middle part, where we had concluded that it is a bifurcation where a period 1 orbit remains stable, period 1 orbit. Like it hits the border and remains stable as a period 1 orbit. So, this is mu and this is x. Well, there are complications because that does not prevent the existence of the period 1 orbit, does not prevent the existence of coexistence of high periodic orbits. So, let us consider, will any period 2 orbit exist here? In the last class we have seen that the condition for existence of the period 2 orbit is that it is below this and it is above this. We have seen that, I am not repeating. The condition of existence of period 2 orbit is that tau L is greater than minus 1 plus delta L and tau R less than minus. That is the condition. We have already seen that, and since we have seen that, I am not going into the details of it. So, we do not expect the period 1 orbit to exist here, because it exists above outside this range, but that is not true for the period 3 orbit, that is not true for the period 4 orbit. So, we will need to consider these existence of these orbits. How do you probe whether or not a period 3 orbit will exist? The period 3 orbits existence will be given by, suppose this is the state space, and there will be one point here, another point here, and a third point here. So, this point will map to this point, this point will map to this point, and this one will map to this point. This can be a period 3 orbit, or so this point will map to this point, this point will map to this point. What is the distinction? It is having, this orbit is having 2 points to the left and 1 to the right. We will be calling it LLR orbit, and this orbit will be having 2 points to the right and 1 point in the left. So, it is called LRR orbit. So, when we talk about the period 3 orbit, it could be either of the two, and we will need to talk about both. We will have to find out where both will occur. How will you do that? That is algebraically pretty straightforward, but you might need to do some algebraic manipulation in order to actually obtain it. So, what we will do, you will start from this point, apply the left hand map once, apply the left hand map another time, and apply the right hand map again, to ultimately come to x3, and then you would say that x3 is equal to x1. So, you will then solve the equations in order to obtain the position here. Similarly here, similarly here. Okay. Similarly here, you will find, you will apply the left hand map once, right hand map again, right hand map again, come back here, solve it. That way you can solve for each of these points. Okay. Once you do so, what you have obtained? You have obtained the positions of these individual points. Out of that, one you can ignore because it will be immaterial. For example, this point in the right hand side, that will always be in the right hand side, that cannot go to the left hand side. If it does, then all the points of a period 3 orbit will be left hand side, which is impossible, because the left hand side is a linear side. In a linear map, you cannot have a high periodic orbit. Similarly, this point cannot go to the right hand side. So, it essentially boils down to finding the locations of these two and imposing the condition that both these x coordinates should be negative in this case and both these x coordinates should be positive in this case. Okay. So, if we do that, then we can find out the range of parameters where this will exist and this will exist. Okay. Similarly, we can obtain a period 4 orbit and so on and so forth, and it may so happen that some of these will occur somewhere here. That means, just imagine that suppose a period 3 is occurring here. What does it mean? Suppose a period 3 is occurring for mu greater than 0 here. Suppose, if you actually do this, you will find a large number of such regions where other high period orbits will occur. But just try to imagine what will happen, what we will see when we change the parameter mu. We are changing the parameter mu, and there was a periodic orbit that came and hit the border. In the other side of the border, the periodic orbit, period 1 orbit remains stable, and so we will draw it something like this. But at the same time, the other period 3 orbit has been will exist in this side. That means, this fellow will be something like this. Okay. Now, imagine such a thing is happening in a practical dynamical system, and you are changing the parameter, like say in an electrical circuit a voltage, in a mechanical circuit some applied force or something like that, something representing the parameter mu. You are changing it and it is moving like this, and finally it hits the border. Just following it, what happens? There are 2 orbits, one period 3, one period 1. If there are 2 orbits, 2 stable orbits, they should have their own basins of attraction. So, each one will have its own basin of attraction, but you see the character is that the more closer to the value of mu is equal to 0 you go, the closer these points are, and at mu is equal to 0 they are actually at the same point physically, and then they move away from each other and they have their own basin of attraction, right. Now, every physical system has some ambient noise, you can't help it. Every physical system will have some noise. As a result of that noise, it will go on slightly moving, not exactly following this particular small line, but slightly moving around it. Now, here it encounters a situation that there are 2 basins of attraction, but they are arbitrarily close to each other, and the noise is stronger than that. What will happen? What happens is that there is no guarantee in which region will it be, in which basin of attraction will it be. It is moving arbitrarily, randomly, and in that random motion it is intermittently going to this basin of attraction and intermittently going to that basin of attraction, and while it does so, this parameter is changing. So, these basins of attraction are going away from each other, but while they were arbitrarily close to each other, this fellow was randomly moving. So, what does it mean? It means that ultimately when they move away from each other, these basins of attraction, this point, the state point will be in either of the basins, but there is absolutely no guarantee which one will it be. This is another fundamental source of uncertainty. There are uncertainties in various ways occurring in a chaotic system, but this is not a chaotic system, periodic system, but still it has a fundamental source of uncertainty. As you change the parameter, once same system, it will lock into a period 1 orbit here. Another time same system, you do the bifurcation diagram, it will go into the period 3 orbit without any difference made in the actual system configuration, no change in the parameters. Okay. This is called a multiple attractor bifurcation. And these are considered to be somewhat undesirable, because you never know which orbit it will ultimately go in. In any engineering system, you would like to predict that if I make this change in the parameter, it should behave like this, but in the here is a case where you cannot predict, it either goes there or goes here. Now, how to actually find the parameter range in which this multiple attractor bifurcation occurs? You see, it will be either a period 1 with a period 3 orbit, period 1 with a period 4 orbit, period 1 with a high periodic orbit, period 1 with a chaotic orbit, whatever it is, but period 1 plus something. So, I will illustrate how to obtain the range in which the period 1 orbit will exist with the period 3 orbit, because that is something that can be done. And following the same logic, you can find out in which parameter range will the period 1 orbit coexist with the period 4 orbit, 5 orbit, 6 orbit and all that. So, as I said, suppose I am dealing with this LRR orbit and I am trying to find out its value. We can solve the equation and we can obtain the value. I will write, you can easily check, but it will be advisable if you redo the thing so that you can obtain it independent of my writing on the in this paper. For the LR or RR orbit, the solutions, there will be two equations given, two conditions. One, this fellow become equal to 0 and another, this x coordinate become equal to 0. These are the two conditions. If you write, it will be like this: 1 plus tau L minus delta R plus tau L tau R plus delta L delta R plus delta L tau R whole with mu divided by 1 plus delta square R delta L plus tau L delta R plus delta L tau R plus delta L delta R tau R minus tau R square. May look formidably large and complicated, but do not get worried about it. Obviously, there will be another equation which will be similar. It is 1 plus, in place of tau L it will be tau R minus delta L plus this is symmetrical plus this is symmetrical plus delta R tau L whole mu divided by 1 plus delta R square delta L plus tau L delta R plus delta L tau R plus delta R no, this tau L tau R square, this is greater than 0. Obviously, the range of existence of this orbit LRR orbit will be delimited by these two conditions. Now, here is a number in the numerator and here is a number in the denominator, and both are to be equal to 0 for the condition, or greater than 0 for the condition that it will exist. So, obviously, this will be positive if both these are positive or both these are negative. Similarly, this will be positive when this and that both are positive or both are negative. This immediately tells you that this condition and this condition, notice the two denominators are the same. They actually, these two lines, this condition equal to 0, this condition equal to 0 and this condition equal to 0, they delineate the range of the parameter space. So, this will give an equation, a line, this will give a line and the denominator will give another line. These three if you draw, you simply get some kind of a area, So, you can say that this area will be representing the range in which this fellow exists. Okay. So, if you place the initial condition there or the parameter there, then you know that in this parameter range I can expect a multiple attractor bifurcation. So, if say you have obtained a bifurcation diagram looking something like this, you are happy that it was a periodic orbit and it remained a periodic orbit, but as I told you, you have to obtain the Jacobian matrices and then you have to fit to the theory, and after having put these trace and the determinant into that picture, if you find that it falls somewhere here, you know that even though I have not detected it in the bifurcation diagram, this fellow exists, lurks somewhere. So, I am in a dangerous situation, right. So, that is the power of the theory, that we can from the theory anticipate that no, even though I do not see it, I am in a dangerous situation. Similarly, you can obtain the condition for existence of the period 4 orbit, period 5 orbit, 6 orbit and all that, and all these will represent the multiple attractor bifurcation conditions. Now, these are understood to be problematic, but there is another situation that is understood to be dangerous. That is when there are two attractors. Here we are considering one period 1 attractor, another period 3 attractor, but suppose it is period 1 attractor and another attractor at infinity. That means it is another situation where this period 3 attractor is not there, it is an attractor at infinity, but the same multiple attractor bifurcation occurs. That means as you go arbitrarily close to this point, there is another attractor at infinity and its basin of attraction comes arbitrarily close to the fixed point. So, even though if you just look at the fixed point and keep on obtaining or looking at its Jacobian, you will find the fixed point is stable, you are happy, yet its basin of attraction collapses to 0 at the point of bifurcation. That is called a dangerous bifurcation, because simply normally in control theory the eigenvalues are understood to be the indicator of stability, and here is a situation where the eigenvalues give no indication of the stability. If you obtain the eigenvalues, you will find them they are stable, yet the system collapses, because there is always some ambient noise and it has a finite probability that it will go into the basin of attraction of the attractor at infinity, it will collapse. So, it is necessary to understand why that happens and where that happens, because even though this middle part, as I told you, is many people think it is a safe part because it was a period 1 remaining period 1, it is not really the safe part. Let us try to understand it clearly. So, you have seen that these two conditions will actually give 3 conditions, because the numerator here and the two denominators are the same. These two individually are the conditions. Okay. If you plot them, you will get a, say I am plotting in that middle part. So, this is tau L. So, what is this? This is 1 plus delta L minus 1 plus delta L and so on and so forth. this condition will turn out to be like this, and so out of that one is this condition which is here, another is this condition which is here, another is the denominator condition which is there. It is actually single line. So, you can say that fine, I have understood that the LRR orbit will occur in this parameter range. Good. Will it be stable? Will it be stable? Well, the stability condition is a bit different, because the stability condition, how do you obtain? The stability condition is that the Jacobian of the left hand side times the Jacobian of the right hand side times the Jacobian of the right hand side. So, JL, JR, JR, yeah, its eigenvalues should be, that is the condition. Now, if you obtain that, then you will see that one of the condition, eigenvalues can be less than 1, means it could be plus 1 or minus 1. The plus 1 condition is exactly the same as the denominator. Will turn out to be, if you can easily do that, it will turn out to be exactly the same as the denominator. So, this is also the, this line is also the condition for its stability. This side it will be stable. Okay. Fine. So, we understand that it could be stable. The moment I say that it could be stable, the moment I say it could be stable, I understand that it is stable in addition to the period 1 fixed point. So, in addition to the period 1 fixed point, it is a LRR type period 3 orbit is stable. The moment you tell me that, I will ask who forms the basin boundary. If there are two stable orbits, there has to be basin of attraction. So, immediately I will ask who forms the basin boundary, and you know that the basin boundary can be formed only by the stable manifold of a regular saddle fixed point. So, who is that regular saddle? Where is that regular saddle? In fact, all these orbits will have a complementary orbit. Complementary orbit means if it is a LRR orbit, then take one of the symbols to the left, then whatever orbit you get, it is a complementary orbit. So, LLR orbit is a complementary orbit. So, first suspect is that is there a LLR orbit? Yes, in fact, there is a LLR orbit. If you really investigate, you will find that there is a LLR orbit, and that is what forms the basin boundary. So, naturally, we will try to find out, okay, where does this orbit exist? The moment we try to do that, we find that this fellow exists over a range. You will do by exactly the same procedure. That means, for the LR orbit, again you will find similar conditions. I am not writing that, it is not necessary for me to write all that all the time, but if you do that, you will find that that exists over a condition that is like this. Okay. And namely over a larger range. So, notice what I have said that there is no reason to think that the LR orbit and LRR orbit will occur for the same range, because these conditions will turn out to be different. If the conditions turn out to be different, obviously the orbit's region of existence will be different, because you are solving different equations, and the difference is manifested mainly because the stability conditions will be same. So, here it will be a different number, different range, different line. What does it mean? It means that if I place the parameter here, then I have, can you see where I have placed it here? Then I have the coexistence of the period 3 stable point and the unstable point, because the LR orbit at that point is unstable. So, I have the condition the LLR orbit is a regular saddle its stable manifold is forming the basin boundary. Happy. But okay, have you understood this condition? This condition is where period 1 orbit is there, period 3 stable orbit is there, but at the same time period 3 unstable orbit is there, which is a regular saddle, and at that point it will be unstable. So, that unstable regular saddle points stable manifold will form the basin boundary. Simple case. What happens here? Notice if I place the parameter here, then the period 1 orbit is there, the period 3 unstable orbit is there, but the period 3 stable orbit is not there, because the existence condition has not been satisfied yet, right. It will be satisfied when you move here, but here it is not there. What does it mean? It means that there is only the existence of a period 1 stable point and a period 3 unstable, but the unstable point is now a regular saddle. It will have a stable manifold, and all stable manifolds of regular saddles form basin boundaries. Basin boundaries between what and what? Yes, one is at the period 1 attractor, the other will be at infinity. So, under that condition it will lead to that situation that I talked of, that there is a coexistence of a period 1 attractor with an attractor at infinity, and if that happens, then the system will inevitably collapse at the bifurcation point, even though the periodic orbit remains stable, because its basin of attraction shrinks to 0 size. Okay, is that clear? So, what you will actually see is something like this. Let me draw it with this. Stable, it was stable, it remains stable, but this stable fellow had a basin of attraction, say something like this, which also scales with mu, and therefore, that shrinks to 0 side. Here also there was a basin of attraction. I am not drawing a chaotic orbit, it is just the basin of attraction, that also scales with mu, and that also shrinks to 0 side at this point. So, at this point the basin of attraction has size 0. So, that is called a dangerous bifurcation. That has no equal, no parallel in smooth systems. Okay. So, in today's lecture we have essentially tried to understand how to apply this knowledge to actual physical systems, and we have in addition come across two possibilities. In brief, so far I have not discussed one possibility which I will in brief discuss, that is, if you have the determinant greater than 1, then what? So far we have not talked about that, we have considered only dissipative systems, but if the determinant is greater than 1, then what? Okay, this condition, since I am running out of time today, I will come to in the next class. This condition, what happens where the determinant is greater than 1. Okay, that is all for today. Thank you. So far we have been considering the situation where the determinant in both the sides of the piecewise smooth map were less than unity. What does it physically imply? It implies that if you take some area, then in successive iterations of the map the area will shrink. Essentially that is the meaning of the determinant being less than unity. The determinant being negative means the area flips to the other side. So, it is like a dish, it flips. But in general we have been considering the situation where you have modulus of the determinant less than unity. Just recall that in case the determinant is negative, then it does not allow a complex conjugate pair of eigenvalues. So, if the determinant is negative, the eigenvalues are always real, either it can be a regular saddle or a flip saddle, or attractors, regular attractor, flip. Is regular attractor possible? No, probably only flip attractor is possible. So, this possibilities we have more or less dealt with. Now, let us come to the situation where which admits the possibility of the determinant becoming greater than 1. Now, obviously, if the determinant is greater than 1 in both the sides, then it is sort of expanding in both the sides. Take any unit area, it will expand in all the subsequent iterates, and as a result the attractor will not exist, it will go to infinity. But supposing it is the system is having one side in which the determinant is positive, under what condition can it happen? For example, in most power electronic circuits, there is a switching, the switch is turned on or off, and that is what gives the piecewise smooth character of the system, right. And we are trying to figure out the physical meaning of the determinant becoming greater than unity. Is it possible in a physical system? Well, just imagine the situation where the switch remains on perpetually. What happens then? Obviously, if the switch remains on and there is only an inductor connected across it, for example, a circuit like this, the power supply is here, there is a switch, and then you have got an inductor here. Why? Because since this side is negative, its implication is that if there is any initial condition in the right hand side, in the next iteration it will go to the left hand side, because of the flipping behavior, it has a flipping behavior. Since any iteration in the right hand side goes to the left hand side in the next iterate, it means that you can only have this orbit, but not this orbit, not this orbit. Okay. Clear? Period 3, you can only have LLR, which means that there will be one range for period 3, one range for period 4, one range for period 5 and all that, and that you can calculate from those equations, and the resulting behavior is like this. There is one range for period 2, one range for period 3, one range for period 4 and so on and so forth, but that will ultimately add up to an infinite periodicity here. Okay. It is a period adding cascade which will add up to infinite periodicity, but here infinite periodicity will not imply a chaotic orbit. Is that clear? It is a bit tricky, because we had earlier said that the chaos is nothing but a aperiodic orbit. This is also a aperiodic orbit. Infinite periodicity means aperiodic orbit, yet it is not a chaotic orbit. Why? Because since every part of the parameters or the state space is contractive, the Lyapunov exponent must be less than 0. If it is less than 0, this fellow, even though it is a high periodic orbit or infinite periodic orbit, it is not a chaotic orbit. Okay. So, with the details we will continue in the next class. Thank you.